All right, so this is a math video intended for mathematicians and anybody that loves math and is also interested in the physics of math or math that relates to physics. So if you're just someone that likes math and you know some mathematicians, share this video with them. If you're somewhere in the middle there where you're a teacher of math, but you know someone sort of who's more authoritative, show this video to them. There's a lot of good information in here. There's a huge jigsaw puzzle piece of mathematics that's been missing in base 10 that exists in base 12. I'm introducing you to something I'm calling the Dozenal dodecagon. It's a geometric pattern that is anchored and emerges from the base 12 Cartesian plane. We can't see it in base 10, but it's a very important foundational geometric pattern, and it needs to be acknowledged and introduced to the mathematics community. So that's what the intention of this video is to introduce you to this geometric pattern and why it's important. It has an aspect to the geometry of the circle, so incredibly foundational, that's missing again in base 10, and ultimately we can use it to divide the circle perfectly into 360 degrees and then more. So that 360 degree diagram sets the stage or the underneath framework upon which we continue that dividing of the circle into smaller and smaller sections with perfect symmetry. And then when we do that, eventually what emerges from this geometric pattern is a base 12 or Dozenal version of pi that has different qualities than base 10. So that's all very controversial stuff and it sounds pretty heady, but that's exactly what I'm going to be able to do in this video. This is a discovery, not an invention. I'm not trying to sell you something, but simply show you something that already exists on the base 12 Cartesian plane. So it's very important. And so here we go. All right, so in this presentation, because it's on a base 12 Cartesian plane, the math has to be in base 12. I'm going to do my best to sort of straddle base 10 and base 12 and present most of the numbers as fractions of 12 in base 10, so keeping it from a base 10 point of view, but there are going to be some examples where we're using base 12 math. So I just want to give you a quick example of some of the numbers that you're going to see in base 12 and just what it looks like. So 6 plus 6 equals a dozen, or a dough. I'm going to be referring to a dozen as dough in base 12. When we count, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, dec, L, and dough. So 4 times 3 is dough. 5 squared equals 2 dough, 1. So 2 groups of 12 plus 1. 7 squared, 4 dough, 1. 4 squared, 1 dough, 4. 9 times 2, 1 dough, 6. 5 times 2 equals dec. 5 times 3, 1 dough, 3. 5 times 4, 1 dough, 8. 0.96 divided by 2 equals 0.49. 0.96 multiplied by 2 is 1.7. Okay, so those are some numbers and equations that we're going to encounter in this presentation. So I just want you to be clear, we are going to be doing all the math in base 12. Okay, so now we're looking at the base 12 Cartesian plane, or the Dozenal Cartesian plane, which is precisely the same as the base 10 Cartesian plane in that the length of 1 is exactly the same, but within that 1 by 1 square, we're dividing that area into twelfths instead of tenths. So what that looks like here, we have a length of 1, and on this side we have twelfths, and on this side we have tenths. So you can see that a twelfth is a smaller unit than a tenth. So that's pretty straightforward. So what that results in is more lattice points, more points that are defined by the horizontal and vertical lines, and the geometric pattern that I'm sharing with you is created by essentially connecting specific lattice points on the base 12 Cartesian plane. So this pattern that you see here, all of these dots are specific points that are lattice points that exist on the base 12 Cartesian plane, and they're not as easily accessible in base 10. So that's the real key to this entire diagram, is the fact that it's anchored on the base 12 Cartesian plane in a way that it can't be in base 10. All right, so now I'm going to introduce you to the Dozenal dodecagon. We're going to plot certain points on the base 12 Cartesian plane. We're going to go over the length of 1.1, put a point there. Then we're going to go over the length of 1 and up 0.7, plot that point there, up 1 over 0.7, plot that point, and then 1.1 and plot that point. So you can see it's very symmetrical around the 45-degree line. We're going to focus on this quadrant of the Cartesian plane, but of course we can do the same thing on the other 3 quadrants. So what's the distance between these points? So we can see here between that and that, it's the length of 0.5 root 2. What's this length here? We're going to go over to the side of the board here, 0.5, 0.5, 0.5 root 2. That other triangle that was colored in has the length of 0.1 and then 0.7 either side of the right angle. What's the length of C? 0.7 squared is 0.41. 0.1 squared is 0.01. Add those together, we get 0.42. So our length of C is the square root of 0.42. Is that the same as this? 0.5 squared is 0.21. Square root of that times square root of 2, square root of 0.42. So we can see that all the sides of this dodecagon are precisely the same length. So the growth pattern of this dodecagon is such that there's the first ring. It's all one length of 0.5 root 2 for each section. Here we have 2 times that. This length is 2 times 0.5 root 2. Here it's 3 times that, then 4 times that. So that's the growth pattern of the dodecagon in units of 0.5 root 2. So next we want to look at the length of this middle line where it is intersecting that section of the dodecagon. The length from here to there is the length of 0.96 root 2. So the coordinates of that point there is 0.96, go over 0.9 and a half, and then up 0.9 and a half. You can see again this line here is perpendicular to the 45-degree line. So we are building our dodecagon, or the dodecagon is already built in units of square root of 2. I'm going to refer to this as the diameter, or the radius and diameter of the dodecagon. And of course, this is the perimeter. Okay, so now what we're going to do is look at the slope of this line here. As we can see, it goes over 1, up 0.7, over 1, up 0.7. So we want to look at the relationship of this line to the 30-degree line, or the relationship of this triangle that's formed to the special right triangle. So when we go over here, here are the dimensions of the special right triangle, 1, 2, square root of 3. Here are the proportions of the triangle that's formed here, where the bottom is the length of 1. This is the length of 0.7, which we know now is the square root of 0.41. Hypotenuse, square root of 1.41. So we want to see what this triangle looks like when it has a base of 1. So we divide everything by the square root of 3, 1, and then here, 1 divided by the square root of 3 gives us an answer in base 12 of 0.4, or the square root of 0.4. So we can see that's less than the square root of 0.41. So we know that this triangle here, the 30-degree angle, is just on the outside of this line here. And just for clarity, what I've done is the example of 4 times this triangle here. So when the base is the length of 4, we multiply this side by 4, which is the square root of 1 do 4. So 1 do 4 times 0.4 gives us the square root of 5.4. And so we can roughly approximate the square root of 5.4 as somewhere between 2.38 and 2.39. So 1, 2.123, 6 is halfway, 8 and 9 just in there. So that's where the 30-degree line is intersecting this, where the x is equal to 4. So the main point of this is just to be aware that this entire large triangle here is sitting inside of the 30 and 60-degree lines because, again, it is symmetrical on the 45. All right, that's the end of the first video in this series. You can now proceed to part 2.